Here is a single spreadsheet that decides whether a $2 billion chip program ships on time or 18 months late. One page, 20 rows, 5 columns, and it is signed by exactly one person. A modern AI accelerator program has a total bill of materials of roughly $2 billion across its 5-year life. 60 to 70% of that bill is locked in before any engineer writes a single line of RTL. Locked in by one spreadsheet, owned by one role, signed off in one meeting that the CEO does not attend and most senior engineers never see. This is what the system architect decides. The role that is the closest thing the chip industry has to a chief executive of a single program that single-handedly decides whether the chip can be built at the cost the business case promised. Get one row of that spreadsheet wrong, and the program eats $300 million in RESPN, IP license fees, or schedule slip. There is no second silicon to fix it. 4 walls define the system architect's job, and every one of them lives on that spreadsheet. Wall 1 is partition. What goes on this die? What goes on a chiplet next to it? What gets pushed to a separate companion chip? The die boundary is the most expensive line on the spreadsheet. Wall 2 is the IP mix. License from ARM or Synopsys or Cadence. Build from scratch with an internal team. Reuse what shipped on the last program. Each cell in that column has a license fee, a build cost, and a risk number attached. 5 major IPs on a typical AI accelerator. 5 decisions that cannot be revisited. Wall 3 is the power, performance, and area budget. The architect writes a single PPA target at the top of the document, and every engineering team works against it for the next 18 months. Miss the power budget by 10%, and the data center customer rejects the chip on arrival. Wall 4 is schedule. The architect owns the critical path. One IP slip cascades through synthesis, verification, place and route, and tape out. A 6-month slip on one IP is a 6-month slip for the whole program. Walk through those 4 walls and you understand why this role decides everything. Wall 1, partition. Picture a blank rectangle, 800 square millimeters at 3 nanometer. The maximum die a foundry can manufacture. The architect has to decide what fits inside and what gets pushed out. Monolithic puts everything on one die. Highest performance, lowest cost per transistor, but if any block fails, the whole die is scrap. Yield drops exponentially with die size. Chiplet splits the design across multiple smaller dies, connected through advanced packaging. Each die yields better. Each die can use a different process. The compute tile can be 3 nanometer, while the I/O tile stays at 6 nanometer, where it is cheaper. But the packaging cost is real, and the interconnect protocol between chiplets is now a problem the architect has to solve. Then within the die boundary, the architect picks what gets hardened. A hardened block is laid out by hand or by a specialized team, gets the best power and area, but cannot be changed after first silicon. A soft block is described in RTL, can be modified late, but takes more area. Hardened CPU cores, soft accelerators, hardened SerDes, soft control logic. Every choice has a multi-million-dollar consequence. The partition decision is made in the first 6 weeks of the program. It is the line on the spreadsheet that is hardest to unwind. Wall 2, the IP make versus buy spreadsheet. This is the row that gets the most stares in the architecture review meeting. Take the CPU cluster. The architect can license ARM Neoverse cores. Royalty per chip shipped, around 1 to 1.5% of selling price. Verified silicon, software ecosystem already in place, or build a custom core internally. 20 to 30 engineers for 2 years, no royalty. But if the team misses performance by 20%, the program is dead before tape-out. Take the SerDes. License from Synopsys or Cadence. Pay $7 to $15 million in license fees per process node, plus per chip royalty, or build internally. SerDes is some of the hardest analog design in the industry. Building it in-house means hiring 5 to 10 mixed signal engineers and giving them 3 years. Most architects choose to license. Take the memory controller. License a DDR or HBM controller IP. Pay the license, integrate the verification IP, ship in 12 months, or build. HBM controllers at 3 nanometer are at the edge of what the industry knows how to do. One bug in the training sequence, and the chip never sees its main memory. 5 major IPs, 5 decisions, roughly $100 million in license fees on a typical AI accelerator. Roughly $300 million of internal engineering cost if the architect decides to build instead. Wall 3, the PPA budget. The architect writes one number at the top of the chip specification document: maximum power, 700 watts. Target frequency, 2.5 gigahertz at typical voltage. Total die area, 600 square millimeters. 3 numbers. 200 engineers will spend 18 months trying to hit them. The budget cascades downward. The CPU cluster gets 120 watts. The accelerator engine gets 400 watts. The memory subsystem gets 100 watts. The I/O and SerDes get the remaining 80. Each team takes their slice and breaks it down further. The DDR controller team gets 20 watts of the 100-watt memory budget. The HBM PPA gets 50 watts. The internal fabric gets 30 watts. Now multiply that down to the block level, then to the gate level, then to the transistor level. Every engineer in the program is, in effect, optimizing against a number the architect wrote on day one. Halfway through the program, one team comes back and says they cannot hit their power number. The accelerator engine is at 420 watts instead of 400. The architect has 3 choices. Steal 20 watts from another block, which means that block must shrink performance. Push the chip past its power envelope, which means the data center customer rejects it. Or change the partition, which means going back to wall 1. The PPA budget is the most cascading decision on the spreadsheet. Every change in one cell ripples through 20 others. Wall 4. Schedule. 18 months from architecture freeze to first silicon. Pick the wrong critical path and you ship in 24. The architect builds a dependency graph. RTL freeze gates verification. Verification gates physical design. Physical design gates tape out. Tape out gates mask making at the foundry. Mask making gates wafer fabrication. Wafer fabrication gates packaging. Packaging gates first silicon in the lab. Every IP block sits on that graph. If one block slips 2 months, the entire program slips 2 months. There are no parallel paths around it. Foundry slots are booked years in advance. Mask costs at 3 nanometer are $20 to $30 million per set. You do not retape unless you absolutely have to. So the architect spends most of the program managing risk, which IP is most likely to slip, which vendor has missed their last 3 milestones, which internal team is understaffed. The architect runs weekly reviews of every block, sleeps poorly the night before tape-out, and signs off on the final database knowing that if anything is wrong, the program eats 3 months and $10 million to fix it. Getting wall 4 right is what separates architects from senior engineers. It is the wall that requires judgment, not just analysis. And it is the wall that AI cannot replace. 3 reasons the AI hype cycle has not named this role, and the 2-layer winner that profits every time the spreadsheet gets signed. Reason 1. The architect's work product is decisions, not artifacts. There is no RTL, no schematic, no test pattern with their name on it. The output is a spreadsheet, a slide deck, and a specification document. Hard to demo. Hard to put in a product launch keynote. Reason 2. The decisions look obvious in hindsight and impossible in the moment. Picking ARM for the CPU cluster, picking 3 nanometer for the compute tile, picking CoWoS-L packaging. 3 years later, it looks like the only choice anyone could have made. At the time, each was a fork in the road with hundreds of millions of dollars on each branch. Reason 3. AI cannot make these decisions because they require predicting which IP vendor will deliver on schedule, which foundry node will yield well in the year you tape out, which customer's workload will shift between architecture freeze and product launch. That training data does not exist in any model. Now the verdict. There are 2 layers. Layer 1 is the architecture IP that gets baked into the spreadsheet on day 1. The winner is ARM. Every major AI accelerator, every data center CPU, every mobile system on chip uses ARM cores. The royalty is small per die, around 1 to 1.5% of selling price. But every advanced chip pays it every quarter for the entire product life. Switching cost is catastrophic. Layer 2 is the architecture decision tools. The winner is Synopsys. Their platform architect product is where the system architect models the chip before any RTL exists. Their IP catalog sits one click away inside those same tools. Once the architect models the chip in Synopsys, the recommended IP comes from the Synopsys catalog. The decision software pulls the decision IP behind it. Both layers profit per chip designed and per chip shipped. The system architect makes the call. ARM and Synopsys capture it for life. Two software-grade margin businesses that nobody outside the chip industry has heard of. Riding on one signature on one spreadsheet. That is the system architect's job. One spreadsheet, $300 million per wrong row. 18 months you cannot get back. Next episode, the Foundry interface engineer. Architect decides what to build. Foundry interface decides whether it can be built at all. Subscribe so you do not miss it.